start. It's a pleasure to introduce our seminar speaker today, Ismael Pérez Fournón, who is going to present us a work very recently published in Nature. And well, a couple of things about Ismael's CV. He did the PhD at the Max Planck Institute in Bonn, and he started as a staff of the IAC and Universidad de La Laguna in 1985. He has participated in a few of the major space infrared extragalactic surveys. For example, first with ISO, LIS, then with Spitzer, SWIRE, and other instruments, and now with the Herschel Space Observatory, in particular with HerMES and HFLS3. He's co-I of the Herschel Space Instrument Consortium and is member of the science team of the Spica and Safari Instrument Consortium. And now he's leading the observation of HerMES high-redshift sources with the GTC, IRAM, and other telescopes. So, Ismael.
So, thank you. It's a pleasure to describe and discuss these results with you. This is a paper published in Nature last week, published online on the 17th of April. It is the first author of this paper is Dominique Richards, who did a lot of the work on the coordination of this project. Most of the work was done while he was postdoc at Caltech, but now he's professor at Cornell University. And this is part of the HerMES project. This is what I plan to talk about today. A quick introduction of the subject, then describe how we found this object, detecting the most distant massive starburst galaxies with Herschel, then some discussion on how unique is it, do we expect to find more, have we found more, do we expect to find more in the Herschel data. I will describe briefly what we did on this object. A lot of observations with a lot of telescopes, a lot of integration time, many proposals, many DDT director's time proposal, including IC DDT time. I will describe the main results and then discuss a bit what we plan to do next. And I give you here some numbers. This object was not known for the public, was known internally in the consortium, obviously, but we kept it very secret. Only the telescope allocation times panels did know about this object, and maybe some of our colleagues. But now if you type in Google HFLS3 and then type Galaxia and Galaxia, because otherwise you could get something funny, but it's forced that you find the two words. I did this morning, so about 4,000 pages mention this in Spanish, about 9,000 pages mention this in English. So it's incredible how news propagate these days in the internet. So a few words about HerMES. There are several things called HerMES, but in our case, HerMES is the Herschel multi-tier extragalactic survey, an astronomical project to study the evolution of galaxies in the distant universe. It is the largest project on ESA's Herschel Space Observatory. By the way, I should mention that Herschel is dying, so there is helium maybe for a few hours, for a few days, but not more than 2 weeks. So in a few weeks, we will not have any mission like Herschel for the next 10 years, who knows. This project is carried out by a large team made up primarily of people who built one of the instruments of Herschel called Spire. It is a guaranteed time key project of the Herschel Spire instrument team. The Spire PI is Matt Griffin from Cardiff University. HerMES is coordinated by Seb Oliver of University of Sussex, Jamie Bock, Caltech. And this first paper on this source has been coordinated by Dominique Richards, Cornell, and Caltech. People from my group that are co-authors of this paper is Paloma there, Alina, Patricia, who's now not anymore in the Institute, Antonio Cabrera-Laves from GTC, and myself, and Nicolas Laporte, who started recently, is also involved in ongoing studies of this object. So this is the snapshot of the Nature paper. 64 authors, I think, 32 institutes. And I'll explain later on why so many authors and how many institutes in particular. So as a sort of introduction, massive present-day early type galaxies probably gain the bulk of their stellar mass and heavy elements through intense dust and shrouded starbursts. That is, increased rates of star formation in the most massive dark matter halos at early epochs, but we don't know really how early. So however, it remains unknown how soon after the Big Bang these massive starburst progenitors exist. Until now, the measured redshift distribution of these dusty massive starbursts has long been suspected to be biased, low in redshift, because of selection effects, as confirmed by recent findings of systems with redshifts as high as 5. So we are not alone in this business. Our competitors really comes from the South Pole telescope. There is another survey doing similar things, but at millimeter wavelengths with a telescope in the South Pole, and they found several objects similar to ours at lower redshifts, but they are lensed. The majority of those objects are lensed by gravitational magnified by gravitational lensing. In our case, this object we think is not strongly magnified. So what about the other galaxies at redshift higher than 6? So redshift 6 is not so sexy, let's say, these days. So we now know well how to find and study normal galaxies at redshifts higher than 6. This has been done in the ultra deep, deep Hubble fields, in deep and wide fields like Woods that Nicola is working on, in deep or even wider fields like the ones of Chris Willott et al. Chris was postdoc here, and last year published a paper on this population. He's now in Canada. So, but all these galaxies are small, and they have very low masses, low luminosities, low star formation rates. So the thing we have found was not expected. No model, no prediction predicted such a massive high luminosity source at very high redshift. So the known ones before these ones are faint at all wavelengths, and therefore are very difficult to study. So that's one of the reasons to build the ELTs, telescopes, and so on. They are very faint. They are faint in the radio as well. They are faint in the millimeters. So what I'm going to show you is impossible to do with this normal, or is much more difficult to do with normal galaxies. And the other point that I want to address is that the deep fields that we have developed in the last decades, I mean, with Hubble, with Spitzer, with Herschel, they may be in the wrong areas of the sky to find the most massive galaxies and structures in the universe. Because the way you define a deep field like the Hubble deep fields is just look at a piece of sky that there are no bright stars, no bright radio sources, no bright whatever, and then you integrate deep. But in the cosmic web, you may be pointing, well, randomly. So you are not picking up the massive structures. Maybe with the deep and wide surveys that these years are starting, that's not the case. But with the classical deep fields, that's a problem. So I'll summarize first the first results on this study, and then I will explain how we came to these conclusions. We report here the identification of a massive starburst galaxy of redshift 6.3 through a sub-millimeter color selection technique. The redshift is clear. The redshift is much better than the redshifts of nearby galaxies that we know. So the precision it comes from a suite of molecular and atomic fine structure cooling lines. And these measurements reveal 100 billion solar masses of highly excited, chemically evolved interstellar medium in this galaxy, which constitutes at least 40% of the baryonic mass. A maximum starburst converts the gas into stars at a rate more than 2,000 times that of the Milky Way, and a rate that is among the highest, if not the highest, observed at any epoch. So the conclusion is that despite the overall turndown in cosmic star formation from other studies towards the highest redshifts, it seems that the environments mature enough to form these most massive intense starbursts existed in the universe at least as early as 880 million years after the Big Bang. And this was completely unexpected. So I'll explain a bit. For many of us, it's quite clear, but many not for all of you. This is the so-called K correction, that negative K correction that was suggested by Blaine and Andrew Blaine and Blaine and I remember later. In many years ago, basically, if you take a local spiral template like M100 and you, with the same luminosity, you move it to higher redshifts, then you have there redshift 0.1, 1, 2. So at redshift, these three bands, blue, green, and red, are the blue, green, and red bands of spire, centered at 250, 350, and 500 micron. So the majority of the sources in the local universe are blue in these bands. So they are brighter at 250, then less bright at 350, and relatively faint at 500. But when you move to higher redshifts, then the SED, so if you are somewhere here, then you start to see red objects. So that's what we call red objects. So it's not red in the optical or in the near infrared, it's red in the spire bands. That's what we call red in this study. So, but these objects are very dusty. So one of our collaborators, one of the co-authors of this paper is Scott Chapman. Scott did a very nice job in the early 2000 to 2005 with the Keck, the beginning of the Keck telescopes, studying this population, but selected in the scuba bands. The problem was that the positions were not good, so they require radio identification to pick up the possible counterparts. And that is the bias. By doing that, you're biasing the population. So he concluded, or he and his collaborators concluded, that the majority of these scuba galaxies were at redshift 2. Now we are talking about redshift 6. So why was this population not found before? Well, because we didn't have Herschel before. So the idea here is to look at the population, the very, very small fraction of the objects that are candidates to be at redshift higher than 4, and that they are red in the Herschel spire bands. So can we develop an efficient technique to ID these very high dusty starbursts? And then if we find them, how can we be sure that we get the right redshift, that we get the right ID, etc.? Here I have put a figure on, this is a project that is starting this year, I think has funding to start. This is the telescope that is going to be at the highest elevation on the Earth, the Cornell Caltech Atacama telescope. We have discussed in Spain the possibilities to eventually become involved in this project when the funding situation improves, hopefully. So this will be, let's say, the Herschel on Earth, similar to Herschel on Earth, doing similar related bands, the bands that can be studied from the Earth. And the other telescope similar to this is the Large Millimeter Telescope that is also in Mexico, that is starting the operations. So let's see if this works, how this works. Okay, this is like the Herschel Hasbro diagram for these sources. So this is basically combining, nothing to do with stars, but this is dust, what we are studying here. But this is just a plot of the flux ratios, 500 to 350 versus 350 over 250. And so if we plot all the Herschel objects, most of them are down here. They are blue in this diagram, so we are not interested in those for this study. So we are interested in this stream population. Very few objects in that part of the diagram. But apart from this study, you see the error bars are very large because it's not easy to measure the photometry from the Spire images, particularly for relatively faint sources. But apart from this one, we know now of 5 or 6 more sources at redshifts higher than 4. In most cases are part of our study. In other cases are studies by other groups, by Herschel Atlas, and one serendipitously found in the Herschel Legacy Survey in Abel cluster, Abel 773. And the lines are the tracks of popular far-infrared templates in this color diagram. Depending on the dust temperature, depending on the actual shape of the SCD, so you have different predictions. And now we are building our own template based on the objects we know at these redshifts. But don't forget that even if Herschel is much larger in collecting area than Hubble, the angular resolution in the Spire bands is pretty poor. So it's 18, 25, 36 arcseconds in the 3 bands. So this is not easy. So we know the objects, but now how do we understand them? How do we know these blobs, what they are? So this is a very small part of one of our first fields. This is actually one of the first fields we observed with Herschel. That was also one of the first fields, well, the first field actually observed with Spitzer. So the name comes from Spitzer, first look survey. That was the Spitzer first look survey field. Now it was not the first for Herschel, but it was one of the first ones. This is part of the science demonstration phase observations that we carried out 3 years ago. So according to the best models based on the Herschel population at lower redshifts, the density of massive starburst that we expect to see at redshift higher than 5 is about 1% per square degree. So very few sources. We should expect to see something like this, the ones I'm going to show you, over areas of the sky of 70 square degrees, but not over an area like this of 7 square degrees. So we define these very high redshift candidates as ultra-red, not only red, but ultra-red. So we force that the 350 micron flux is less than the 500 micron divided by 1.3. Okay. In this study, we found many more sources than expected. So about 1 every 4 square degrees. So over the whole area of the sky observed by Herschel, we expect them to see about 240 objects. Herschel has observed about 1,000 square degrees if you combine all the surveys. So let's see what we did to get the redshifts. Only by combination of many facilities we were able to be sure that the redshift was correct. I will show you. So this is a very small part of the Spire FLS image, HerMES FLS image at 250 sources here and there. Then 350, suddenly there is something there in the middle that starts to become brighter. And then at 500 is much brighter than the rest. So this is the sort of sources that we are looking at. And we describe it like looking for needles in a haystack, buscar una aguja en un pajar, no? Hundreds of thousands of sources, and we are interested in things like this. Okay, let's see what we did. We did first some millimeter interferometry with a some millimeter array. In this case, it's more than that. In this case, it's a compilation of all the different observations that we have done with different interferometers, including Plateau de Bure and Karma. But the first one was one of those images with SMA. I think it's the one on the right, to the right, at 880 micron. So we then knew very precisely the position of the dust obscure object. So is there any optical emission associated with that? Is there any infrared emission associated with that? We didn't know. I observed this object with at the William Herschel first with ACAM in a DDT night, IC director's time, and we saw something close to the interferometric position. And initially we thought that was the ID, but that was very difficult. And at that time we didn't know the redshift. At that time we didn't know the redshift, the millimeter redshift. At the same time, our Keck colleagues, knowing only the interferometric position, then observe with Keck with ALRIS, a long slit spectrum, aligning the slit with a bright object, this D and C objects there. And then they found this A object is redshift 2.2, and this B1, that is the one that we are interested in, at redshift 2.092. That is the object that we saw with the William Herschel, not the background object. Okay, but we didn't know that yet. So we didn't know the background redshift yet with this observation. So these observations basically found that there is something here at redshift 2. Actually, they didn't have, after the William Herschel images, after knowing the redshifts, we had international time at La Palma, including the GTC telescope. And then I decided to use as much as possible to study this object. And then we took deeper images with GTC, with Osiris, deeper than the William Herschel. That image actually is one of the deepest one in I-band. And there we cannot see the background object because it's heavily obscure. And at the high redshift, we have been able to put limits for the SCD analysis. And we see easily this redshift 2 source. And the redshift together with the optical magnitudes from GTC have been used to estimate the mass of this redshift 2 galaxy and then estimate if it is lensing the background, magnifying the background object or not. And we think that it's not magnifying very much the background object. We don't see any evidence for lensing in the millimeter images, etc. Okay, so next step was let's try to do CO spectroscopy. Karma is an interferometer in California. Dominique was at that time in Caltech. Caltech is part of Karma, so he spent a lot of time observing this object with Karma. And he first found a line, and that line was compatible with one of the CO transitions, 322, at redshift close to the optical object, but not exactly the same. So that was a bit strange. So it should be at the same. If the Keck redshift was good, that one, if the Karma redshift if the Karma frequencies were right, they should be at the same redshift. And this was not at exactly the same redshift, but slightly different. So that could be a wrong identification. So with millimeter spectroscopy, you need to, like in the optical, to have at least 2 detections to be sure that the transition is the one you think you are detecting. So then the strategy was do as much as we can. Let's apply everywhere and vamos a matar la mosca cañonazos, no? Let's kill this guy with all possible observations. So So Herschel was, Spire was first, was part of HerMES, but we applied for PAX. PAX is shorter wavelengths than Spire. Was relatively deep observations. We didn't detect it with PAX. Then more observations with KARMA, with the Caltech Millimeter Observatory, with IRAM, Plateau de Bure, with the 1 millimeter array, IRAM, the 30 meter, and a new bolometer called Gizmo, GTC, the 2 KEX, one for spectroscopy, one for near-infrared imaging with the laser assisted AO system. WISE, we didn't apply for WISE, but we used the public catalogs. And Spitzer, we asked for Spitzer, I think was the DDT time. So with all those observations put together, and we agreed to put it in a single paper. So we didn't want to have 10 papers describing the individual observations. Maybe somebody would not finish their part. We decided to send everything to Dominic, put everything together, and have a high impact paper. And I think that has happened very nicely. So this is now something about we saw the continuum. In the press releases, we have made some emphasis on how massive this source is, how strange it is, how much star formation is going on. But the other aspect is the interstellar medium. We have seen as many molecules and transitions as in nearby objects. This object now has much better data than most of the galaxies that most of you are studying in other wavelengths. So we have a long list of molecular and atomic transitions that we can compare with our nearby universe. And I think that's the most fascinating thing. These are interferometric maps, but now not in the continuum, but in particular transitions, in different CO lines, C+, etc. Water is everywhere in the universe. Even 880 million years after the Big Bang, there was water there. So it's really nice. We haven't exploited that part in the press releases, but I think for me it's one of the nicest results. I mean, water was known in other high redshift objects, redshift 3 or 4, but this is now the highest redshift at which you see water lines. This is one of the instruments that also was very, I would say all the facilities have been important. There is no facility that would say, well, this minor contribution. I think all the facilities have produced very important contributions. But one of them is the Caltech Millimeter Observatory. It's a very small telescope compared with larger single-dish telescopes. But it has a wideband spectrometer called CSPEC. And you see there in the frequency 200 to 300 gigahertz. So it's very broad band. Typically, you have a passband of 3 gigahertz or so. Here is huge. So in a single observations, if the lines are relatively bright, you should be able to see lines and estimate the redshift. So this spectra together with the KARMA initial data, then fix the redshift. So we knew that was the right redshift. So we could continue with other proposals, other studies, but we knew that there was something there, redshift 6.3. Now this is the comparison with a nearby object. Many of you know ARC-220 is one of the redshift 0.018. So it's a very luminous, ultra-luminous object in the nearby universe, very well studied. That gray line is the spectrum from Herschel, actually, spectroscopy using Herschel that detects a lot of CO lines, a lot of water lines. These very high redshift objects, completely different impact in the universe, looks pretty much the same. So we're seeing less than a million years after the Big Bang, a billion, at 880 million years, we see things that are producing stars, have interstellar medium, have molecules, have atoms, very much the same as in our local universe. And since this object is relatively bright at millimeter wavelengths, this can be done. I mean, it's not easy, but can be done. Not easy, I mean that in many cases, integration times have to be long. This is now how the CD looks like, the spectral energy distribution. So we have here, most of the observations have been done here close to the peak. So the peak is slightly above 500 micron, and then the emission comes down to the radio. This is the radio point from the JBLA. So if we compare this object, these are the main properties. I don't have time to discuss in detail, but hyperluminous object, 3 times 10 to the 13, star formation rates of close to 3,000 solar masses per year. So everything there is about 10 times brighter or larger than in R220. If R220 is an extreme case in our local universe, this is 10 times more extreme. If we consider the star formation rate, for instance, imagine all the redshift 5.5 to 6.5, the normal galaxies I was discussing at the beginning, in the Hubble Ultra Deep Field. You put together all those galaxies. I don't know how many they are, but all the galaxies there in that redshift range. This one alone is 5 times more stellar production than all those galaxies average, put together, some. So it's very gas-rich, highly metal-enriched, and it's warm dust, but lower dust optical depth than in R220. If you want to compare it with the Milky Way properties, you can have a look at the table 1 in the paper. There is another column with the Milky Way properties there. So something about the observations at short wavelengths. But by short wavelengths, I mean GTC Osiris, GRI and Z, WST Lyris, K short, and also NIRC2 from Keck. That is not in this figure, but is in the next figure. And Spitzer 3.6 and 4.5. Spitzer still is operating, and differently from Herschel, Spitzer has a mode that can be used in the warm phase that is happening now for the last few years. So there's still capabilities to observe at 3.6 and 4.5 micron. And these are the images on the right here. So what do we see here? We need to zoom a bit to see what we are seeing here. But in the K-band, we see 2 objects. Paloma has become the expert in our group on Lyris reductions and analysis, and she found these 2 very faint objects. And at that time, we didn't have the results from Keck. But when our colleagues sent to us the results from Keck, it was clear what was going on. So we see with Lyris, with seeing limited images, 0.6 per second seeing, basically the same as Keck. And Keck spent, I think, 1 night to do that. We spent 1 hour with Lyris. I still don't understand it, but that's what's going on. With Keck, the resolution is 0.1 per second after corrections for AO. Our resolution was worse, obviously, but the basic thing is already there in the Lyris images. So we see 2 objects separated by about 0.6, 0.7 seconds. One of them is what we call G1b, that is the galaxy that is at redshift 2, that is in the line of sight. And the other one is the very high redshift object. So we are seeing, if you compute what is the rest frame emission, that's UV emission, what we are seeing in the Lyris K short and Keck NIRC2 data. Okay, but apart from this, at longer wavelengths, we can measure many things. This is now the comparison of the dust continuum and the C plus line that is very bright in this object, in general in starburst galaxies, but in particular in this one. These are observations from Thin Plateau de Boule. interferometer. So clearly there is the dust emission is very close to this the southern object seen in the latest images and in the Keck images, and also the C+. So this must be the all of this is coming from the high redshift object. It is compact. It's about 3.5 kiloparsec. When we say huge or large, we are really not telling about the size of the object. For this epoch, it's probably large, but it's not very large compared with today's galaxies. There is high dispersion in the gas properties. No evidence for lensing, or at least not strong lensing. And we estimate that the lensing amplification is less than 1.2, so basically no lensing. And the galaxy is intrinsically very massive and luminous. And if you compute the surface density is very large. And that's why we call this a maximum starburst. So it's the maximum light that you can have in that volume. Otherwise, you would be Eddington limit. You would expel all the gas. I think that doesn't happen maybe it happens in particular sources in the local universe, but not over galaxy scales. And that's consistent with models of the CO, water, and OA station. The gas is warm and dense with high critical density lines pumped by infrared radiation field. And this excitation is consistent with other starbursts, like Marcarentu, and there are no evidence for yet for an HGN. So this is an extraordinary system even compared to typical sub-millimeter galaxies at low redshift. And these are the main properties that we derive for this object. Luminosities in the different lines, in the different millimeter lines, far infrared luminosity, mass of gas about 10 to the 11 solar masses, mass of carbon, mass of hydrogen, mass of dust, dynamical mass. The dynamical mass is measured from the millimeter observations. The dynamical mass is 3 times 10 to the 11. So very massive at those redshifts. Star formation rates about 3,000 solar masses per year, etc. So, is this a unique object, or is it common? We don't know yet, but the two cases I think will change our models on the formation on these galaxies at high redshift. We now have at least one example that is producing stars very quickly, very fast. The total mass is very quickly, very, very high. So if we confirm more candidates, it will impact seriously models of early structure formation. Do we have more? So we have more. We have many candidates. We have several others with measured redshifts, but not at such extreme redshifts. So we have several objects between 4 and 5, as has been described in one of the figures in the paper. So for finding more objects like this, we need better observing capabilities from the ground at related wavelengths, and CCAT is the best telescope that is going to be available in the next few years. So with CCAT, the areas of the sky, the volume of the sky is going to be able to map. There is no limitation like Herschel for 3 years. It can last for a couple of decades, and we hope we will find very many others. But that's not the only facility. So we have started to observe our best cases with HST, with IRAM, of course. This particular case I didn't mention, but it's in the north, so we couldn't do it with ALMA. But whatever is visible from ALMA, we hope that, we have at the moment one project in the queue in the band 2, so it's 10% to 20% priority. We hope to get some objects, but in the next call we will apply again, and we hope to have data from ALMA on a larger sample. Future millimeter telescopes already existing or becoming the construction very soon, like CCAD and LMT. This type of sources will be a very nice case for JWST, but also for the Spica telescope. The Spica is the successor of Herschel. It's a project led by Japan, but also with important international contributions, particularly in Europe. We are contributing with one of the instruments, a far-infrared instrument. It will not go to the Spire wavelengths, but it will cover relatively broad range between 30 and 200 micron. And then obviously for the future optical infrared ELTs from the ground. Finally, thanks to all of you for hearing my talk, and thanks to very many people. I have listed only a few there, the tax that gave us time, the directors that gave us director time, and the very many that constructed the facilities and operate them, funding agencies, and here more locally, in particular to GTC and ING and IRAM in the mainland and in France, staff for all their help to carry out the observations. Special thanks to Jose Acosta, who helped us a lot to get the best out of the latest observations, and also to Antonio Cabrera, who is part of this work, who helped us with the GTC observations. And also I should mention Gabi and Itziar did a lot of work the few days before the press release to prepare the best possible material for the press release. And Gabi quickly produced 2 videos that have been used in some of the press releases of other institutions or other media. And Itziar managed to finish the press release in time. Here is one of the figures that was used in this press release. It was not done by us, was done by our colleagues in the UK, the Cardiff Herschel Outreach Office, and they picked up the optical GTC image, and also on the left, the near-infrared from Keck and millimeter from IRAM. But this image has been used in most of the press releases of our institutions that have been part of this study, and then is copied virtually everywhere. So you see this image, this figure. If you look in Google, you will find hundreds of more places where this has been now used. This is another version that we produced somebody produced and we use in the ISE press release. Very many institutions and magazines like National Geographic had it in their first page for a few days. This was also this figure was also used by our, let's say, big brothers, the Keck people, the two GTCs, also in the Caltech press release. Radio Televisión Española picked up the video and put it in I don't know if they put it on air, but on the web pages it's already there. So this has been, I think, a very nice publicity of what one can do with GTC. It's very short. I have 2 videos that illustrate these results that we put together. Gabi produced very quickly. I'm going to show you. Okay, this is on the facilities that we have used. Obviously space telescopes is not, you don't go there to observe, but many of those facilities where people have gone and done the observations. Not here because plateau is done in service mode. That's the JBLA. There's a some millimeter array in Hawaii as well. The IRAM 30 meter, I went to one of the runs. The William Herschel, the GTC, the 2 Kecks, WISE, upper limits, but still useful, and Spitze. Okay, and thanks to Gabby. And the other one is the other one was done from the figure I show you, but Gabby managed to produce a video from the figure. That is also very nice. Okay. That's Herschel observing the sky. Then we focus on this red dot. Then that's the GTC image. And that's much higher resolution, the interferometric. Blue is gas, red is stars from Keck and Plateau de Peur. Okay, thank you.
Thank you, Ismael, and congratulations on this fantastic work. And we have time for a few questions.
Okay, yeah, congratulations, of course. It's a beautiful work. You have two phases in this work. One is the detection of a candidate and then a lot of follow-up. About the first phase, do you think that the available public databases would allow to find other candidates? You are an expert also on databases.
Yeah, I haven't discussed in detail. We have different methods, and this work has been done also in parallel by the other. Well, there are several other groups that have wide area, so you need wide area first because the density is very small. So you wouldn't see objects like this in the goods fields or in anything that is smaller than 1 square degree or a few square degree. You don't expect to see these objects. So you need wide area. So we had wide area. We did the observations first together with HAtlas. HAtlas is open time. We are guaranteed time. So we are also part of HAtlas. HAtlas has similar candidates, and we are collaborating. So I'm leading, for instance, proposals to IRAM where we, instead of competing, we put together the proposals, or we get the HerMES sources from the HerMES Red Source Working Group, HAtlas sources from Atlas, and then we apply together, share the time. But Atlas has not found yet such a very high redshift, although they have tried. They have tried with IRAM as well. And we haven't done much in the south because in ALMA. The next step will be, I haven't mentioned, but we have a large large program to observe with a bolometer called La Boca on Apex. We are following up some of these sources with Apex. So, but going back to your.
If I go now to my room,
yeah, okay.
I have access to a lot of public databases. Can I look for those?
These images are in the public domain. We have an archive in Marseille called HIDAM, and already in April last year, I think we released the images. I don't remember if we released the catalogs, but probably yes as well. The problem is that we are not finding them directly with the catalogs because in many cases, the majority of the sources are detected at 250 micron. Then our catalogs are based on 250 micron detections. These sources are very faint at 250, so you have to do a different type of search. And there's going to be very soon another paper describing the method. Basically, it's a combination of the images. You put the images at the same scale, the same resolution, then subtract the 250 micron image from the 500 micron. Basically, that's what I showed in the last one of the small images. And then you select the best candidates. Other people check if there are problems or not to identify the best ones. Because you must remember that this Herschel resolution is very poor. So it's a combination of catalogs. We do this work with catalogs, but we do this work also looking at the images. There's a student in Vancouver at the University of Victoria, University of British Columbia, Victoria Osborne, And she's doing this work of putting the images at the same resolution, subtracting, picking up the very best sources, informing the team. And then there's another guy in Colorado, Alex Conley, that puts together all the information, who's doing what, to avoid competition and to avoid duplication of observations. But yes, I mean, part of the work could be done with catalogs, but not probably an object like this would not be found in the normal catalogs, let's say.
Congratulations also for the work, Ismael. Just a question, is this expected to be an isolated object in the middle of nowhere, to say that way, or it will have a cluster of other objects like it around?
That's another of the projects that we are now carrying out. So we applied for, I mean, the expectation is that these massive things should be in the centers of the most massive dark matter halos. But nobody has found that yet. There is evidence of, similar object at redshift 5, something called Aztec 3. Some of the authors of this paper are also involved in that study. So that was published a couple of years ago in Nature as well. But at redshift 6, not much is known. But it will certainly be the typical projects to do with ALMA, with the bolometers on the ground, etc. The problem with Herschel is that we are very close to the confusion limit. So if we look, we have scuba data that is not part of this paper, will be another paper on scuba results. But the idea is that with Herschel, you cannot go much deeper because you reach the confusion limit very, very quickly. But from the ground, you can go deeper. And then the idea is to look for these companion objects if they are also star-forming galaxies. If they're not star-forming galaxies, then you have to do it in the optical and infrared. And we are doing that. So we have HST time that will be sort of planned for August in many different bands with ACS and Wide-Field Camera 3. And we hope to have at least, we'll have the photo series and we'll see if there is any evidence for clustering or not.
Ismael, I think it's very difficult, but have you got any metallicity measurement of this galaxy? Because at this star formation rate, you in principle, in 30 million years, which is nothing, you will form a 10 to 11 solar mass galaxy. So have you got any metallicity indication?
That's what we are. We have metallicity from the millimeter. I mean, all the millimeter bands. High metallicity. We don't have information yet. In the optical is very faint. We don't know what we will see in the HST images, or we will know soon. But the next step that we are going to try is spectroscopy in the near infrared. But that's not easy either.
Ismael, you have repeated a couple of times that this is unexpected.
Unexpected, yeah.
Object. Could you try to tell us a little bit more why you think that is unexpected? Because from my naive point of view, I mean, the large ellipticals are 10 to the 12 solar masses, and they have stars as old as the universe. So if you form 10 to the 12 in 1 giga-year is 10 to the 3 solar masses per year. So why it is so unexpected?
In the scuba times, I mean, people thought that these elliptical galaxies are the scuba galaxies, so, and maybe many of them are scuba galaxies. So you have an intense burst of star formation at redshift 2, and then you build up a lot of mass. But nobody said, okay, something even brighter than the scuba galaxies could happen at redshift. I mean, 880 million years after the Big Bang. All the theories.
But we know that the stars of the ellipticals are as old as the universe. So it's not unexpected that you find things that are forming stars.
Can you give me a single paper? Single paper.
No. I'm not. What I'm saying is, why is it unexpected? That is because no one has observed it before.
I think because the models that fit the rest of the population at low redshifts do not predict these objects. So the models that have been developed in the last years to fit the optical counts, the Spitzer counts, the Herschel counts. Okay, I wouldn't say that they ignore this redshift regime, but basically they produce, they were expecting some galaxies in this redshift range, but not very many.
Okay,
not
thank
very
you.
many. But certainly there must be people now working on models, changing things to produce objects like this.
So congratulations. Yeah. In fact, there are a number of groups already, looking at such high redshifts to find out those sort of objects, redshift 610 even. So this is really amazing. So along the lines of the previous question, it is unexpected within the current view of hierarchical galaxy formation, the modeling, of course. But if you want to build a galaxy, just forgetting about the cosmological context, to explain a massive elliptical, you could do it even with a closed box model. So it's no problem. So let me give you some numbers. For example, what you need to build up a giant elliptical galaxy that is so old is like with a range, depending on the modeling, between 20 and 200 solar masses per year. Okay, with these initial conditions, you can build up a giant elliptical that looks older than, let's say, 10 gigayears, as old as the universe, and in a time scale shorter than 1 gigayear. In fact, shorter than half gigayear. So the numbers we are providing, which could set the initial conditions of those models, it could be even at much higher. Okay, much shorter, much shorter time. So so did you, for example, setting these initial conditions, you can build up, for example, the spectrum of an elliptical galaxy in the present time, for example, Coma or Virgo, whatever, how it will look like. Okay, so this would be an idea to compare with.
But I think the point here, I think what we are now making an impact on modelers, like maybe you, is that this happens very soon and very fast. So while until now we didn't know. Was it gradual over the time? Was it in burst? But maybe later at redshift 2, like the scuba galaxies. Now is at least this object is very soon and very fast. How many are there? How many? And this was with last. We give details in the paper. This would last very little time because at such high star formation rate, the gas will be exhausted in very, I don't know, several million years, 30 million years or something.
We have the last question, I think. Ready.
You said you don't have evidence for AGN yet, and you put the example of Markarian 231 at the local universe. But there are many other Eulers. Markarian is naked. The outflow has blown all the gas in the central region. So what you mean you don't have evidence for AGN yet? What exactly do you mean? Have you run like a...
Well, the only reference range that we have not, I think we have not applied, but we will probably apply next time. Maybe not for the object itself, but maybe for the clustering business, is X-rays. So we have discussed it.
Eulers have an AGN. Most of the Eulers have an AGN in the X-rays. In the X-rays, most of the Eulers have an AGN, as Felier and other people.
At smaller redshifts, you find a combination of AGN and starburst. So could we have this in this object? So maybe, but there is no indication yet from the molecular lines on that. Okay. And we will improve it with more transitions. But at the moment, we don't think there is any evidence for an AGN. But there could be one. I mean, that is so heavily obscured that it's not affecting the rest of the galaxy or something.
Okay, I think we should stop here because coffee is getting cold in the library. So let's thank Ismael again.